Soils are the most important property you're going to have in designing retaining walls. Soil, the foundation, soils are what gives your wall support, where you're going to have settlement concerns, where you're going to have sliding concerns. The reinforced backfill is that zone within the Geogrid area. That's your reinforced soil zone. Turn the water off. You can see when we turn the water off, the void ratio and saturated unit weight went away. If we look at that again, when we have water conditions, we look at the void ratio of the soil, how much are voids, how much are solids, how much is going to be filled with water, and then we have a saturated unit weight. Moist unit weight of 120 pounds per cubic foot, saturated unit weight 138 pounds per cubic foot. So as we get more water in there, the driving force increases with the weight of the soil. When we go to submerged unit weight, it's a saturated unit weight minus 62.4, which brings it down to about 75, which is lower driving force. Another topic. Let's turn the water off. We go in here. Reinforced zone, again, within the geogrids. What we typically assume is a clay soil will be in the range of 26 degrees, 24 to 26 to 28 degrees, depending on the plasticity of the soil. A silt is going to be more 28 to 30. Silt is more granular. It's a little bit more free draining. We don't have the plasticity that we do with a clay. A silty sand is going to be from that silt range, 28 to 30, depending on the amount of the silt is in it. When we go to more of a clean sand and gravel, we're going to be in that 30 to 32 range, and we have select backfill, meaning low fines contents, less than 20% fines, sand and gravel mix. We're going to be in 34 to 36 degree soil. So if we go with a 20, I usually default to 28, on a standard design, a silty sand soil, conservative designed. But it's a choice of the geotech, it's a choice of material that's out there. What we design with unit weights, typically 120 pounds per cubic foot. Granular soil, we can get up to 125, 130, something is well compacted. Maybe up to 125, 130 pounds per cubic foot. Cohesion is that plasticity within the soil. We limit plasticity. We try to put something in, cannot be greater than 50 pounds, and high cohesion should not be used without consideration of tension cracks, effective saturation, etc. So we tend to limit cohesion in the reinforced zone to 0. In the retained zone and the foundation zone, we can up those to 100 pounds. And if we take a look at the results, we do a reinforced design, 10-foot high wall, 10-foot long geogrids. I don't know why they're so long. Oh, right there. Max geogrid spacing. Well, that was 2 feet. Minimum grid length 60%. Something we haven't talked about in preferences is make geogrids the same length. With the NCMA design, it wants to extend the top grid 1 foot beyond the failure plane, and when it does so, it makes all the geogrids that same length. If we turn that preference off, then the geogrids will just follow the failure plane as we go up through the slope. Interesting. But a 28-degree soil, if we go reinforced design, 6 foot, our factor of safety of overturning is 4, but more sliding is 2.48. if we put the retain zone up to a 34, and 34 there for all the soils, we look at static results, 2.48, we updated our design. Look at our factor safety sliding in went up for both at the top of the leveling pad and below the leveling pad. So you can see that that force governs how much our driving and resisting forces are. As we vary the properties of the reinforced fill, you'll see that our tensions in our geogrid go up or down. Like the sector at 610, if we change that to a 28, we go back to static analysis. Remember 610 goes up to 807. Lower the friction angle, the higher the driving force. Direct relationship back and forth. If we put cohesion in there, oops, back to static results, 2.48, we just added cohesion, 3.6, 8.14. So cohesion significantly reduces the driving force. It will also increase your resisting force of sliding on the base, having cohesion sliding at that interface. Leveling pad, if we assume we have a crushed stone leveling pad, that's going to be like a 57 stone, 3/4 inch crush, granular material, 130 pounds per cubic foot. We typically design with that. We can also design with a concrete leveling pad, which is going to have zero friction, but then has a high cohesion, somewhere around 3,000 pounds per 3,000 pounds per square inch, 3,000 psi, and 140 pounds per cubic foot. That will impact the sliding resistance on the leveling pad. There is a little bit difference between a gravel leveling pad and a crushed stone leveling pad. If we do, let's go back up here and look at the Cornerstone permeable. And let's go up to, let's do them all. Okay, there we go, 10-foot high wall. We've got a 5-foot base unit in here. That's stable. If we come in with in a gravity wall design, we don't have any reinforced. We only have the foundation and the retained fill at 27. I'm going to put a clay material in here. Gravity doesn't work. We're failing here in overturning. We're also failing in sliding. We're also failing in bearing. Let me increase my leveling pad depth to a foot. Let me increase my embedment to a foot. We're just still slightly over on bearing. So we will increase our embedment to 1.5 feet. We will get rid of the toe slope. Wow, our bearing is still too large. A couple of things happening here is we're failing in overturning. We're also failing in sliding. We're failing in bearing because we've got a lot of moment, a lot of forces trying to turn that wall over. The option we have in soils, we can use a select backfill, and we'll put a good crushed stone in there at a 36 degrees. So that fills that zone in there with a crushed stone. If we go to static results and we update it, this is all crushed stone in here. Our bearing pressure went down, our sliding increases, and our overturning increases. Because we have a good select material in here, the driving force on the back of the wall is lower, our overturning is lower, our bearing pressures go down, and our sliding works. In many cases where we have poor backfill on the site, clays, silts, very silty material, it's a good idea to come in there with a select soil. We go up at a 45 degree cut, Fill that with a good material, and then our gravity wall is going to work a lot better. You also get good drainage in here, good compaction, much better overall performance. Something we added this year is a friction factor, especially important for slopes down here, is if we have a sand material, then the friction factor, the friction between the base block and the foundation, whether you have a leveling pad or not, would be 0.7. So we can use a friction factor design. Let's go to our static results. We update, look at the sliding 1.99. With the friction factor, our sliding increased because we're looking at sliding as a different factor. Instead of the friction between the two materials, we're using a friction factor approach. Something to consider, if we have clay soils, silt clay, our friction factor is 0.4, which makes sense. That unit now sliding on a clay, which is a slick material. We look at our static results. We go from 2.37 with sand down to a 1.36. We're failing in sliding because we're assuming now that that bottom unit is sitting on a clay or silt soil. We don't have the resistance to sliding. This was something we added this year. Makes a lot of sense. Oftentimes when we design, maybe not cornerstone walls, but other walls, we don't use a leveling pad. Therefore, we can describe what our friction factor is. Some engineers prefer to use a friction factor approach instead of the friction angle approach. Again, it's a preference of the designer, what he wants to use.